Welcome to Architecture and Design Engineering for Performance. In this section, we'll cover some of the important principles that are used for architecture and design for performance. And we'll illustrate the principles through some examples, some of which are real-life examples. So the next few slides show you the basic principles that one needs to apply. These are not theoretical principles, these are actually been derived out of experience, and a number of architects apply these principles for large systems. Now, one of the essential things in architecting a system is to architect for a given cost and to architect for a given hardware investment, where the hardware sizing budget has to be decided upfront very early during the initial stages of the project. Now, how can you do sizing if you do not have the software ready for testing purposes? Well, one of the things that is done is that you start out with the overall performance requirements, with the workload requirements, and then look at the business architecture, see how the business architecture translates to the application architecture. The application architecture in turn will translate to the technical architecture, which is then moved on to a deployment architecture, which has to be sized. And the budget for the hardware and software licensing will come out of the deployment architecture. So essentially what is done is taking the business workload, you translate the business workload to the application workload down to the technology workload. So for example, if your business has 500 banking transactions per second, you will then look at each of the application components and say, well, there will be so many loan processing requests per second, there will be so many logins per second, there will be so many journals per second, there will be so many database writes per second and database reads per second, and so many message communications per second. And then look at your technology that is used to deploy this application, and then say that, well, if there is so many IOs per second, so many database transactions per second on an Oracle or DB2, then what kind of sizing is required for the same, either by looking at public benchmarks available for the same or by looking at past experience of similar deployments on these databases and application servers. The second important point to consider for performance of an architecture and design is that any engineering that is done for performance is something that is not in the realm of code optimization and tuning that is instantaneous. It is more in the realm of long term, where you need that engineering to last for years. So any choice that is made is something that should not be often changed, because it's a very costly change once the system gets implemented. So that's why there is a need for application level performance controls, which we'll see some example of as we progress. But just to correlate it with what happens at a platform level, there are performance controls in your web and application server, for example, number of threads. There are performance controls in your database server, for example, your latches or your database buffers, or in the interface between application and database server in terms of connection pools. Now, these are controls that are provided because the system can be used for a small set of users and should be able to grow to a larger number of users. And same thing can happen at the application level, and you need to figure out what are the appropriate application performance controls so that your options are not hard-coded for a fixed workload. Remember, the workload may grow in terms of number of users and transactions. It can grow also in the mix of transactions. So make sure that there's enough flexibility provided. You also have to keep in mind is that when you come to option 3, anything that is done for performance is not something which is standalone, that you need the fastest Formula 1 racing car. You have to have a solution that is close to optimal but need not be fully optimal as well. You need to always balance between performance and maintenance, because your system has to be maintainable as time progresses, and you don't want an overly complex implementation that is too difficult for a set of people to maintain. You also have to keep in mind that there are a number of design patterns for performance that are available in the market. But just because they are there, they should not be blindly used. I mean, as far as possible, use common sense when it comes to performance engineering. I would say that almost 90 to 95% of any implementation relies on common sense, and there's just 5% that is very specific and needs a good amount of implementation experience. Now, point number 5 is a very important point, that very often people try to use a lot of parallel processing upfront because there is multi-core, because there are a number of servers available cheap, and there is no denying that this should be used. But you have to often look at it that you should always keep parallel processing at the last level of optimization, because in the event that it is used first, you often tend to ignore that there's a lot of basic optimizations that can be done. So the idea should always be that you start out your architecture and design assuming that there's a single thread, and you take that single thread of processing and optimize it to the fullest, so that you can at least look at very often 10x or 20x in a single thread, depending on the right choice of data structures and algorithms that you use in your design. Once you are done with that and you're still far away from the performance requirements, then you look at how do you scale that single thread to multiple threads. Otherwise, you could make a mistake of assuming that you have enough of resources available and processing is the only way to go. No, that's not true. You need to first consider your design through data structures and then look at scalability as a later option. In context of that, people should also keep in mind is that a lot of optimization can be done by choosing right in-memory processing. Given the amount of RAM available in servers today, and given the amount of RAM that is unutilized, it's a pity that many IT projects do not use in-memory processing effectively. In-memory processing can manifest itself either through third-party products, could be in-memory databases like TimesTen, or it could be caches like EHCache. But also, very often you can use your own very simple data structures, including hash maps and trees and heaps, which can be used very effectively to store data, whether it's on the read only, and sometimes you can also store it for data that is less frequently changing. When it is a very highly changing data, then it's better to go in for third-party products. But if it is predominantly static data, you could even use your own data structures for in-memory processing. And usually these would give you to the order of 5 to 10 times at least performance benefits compared to traditional database approaches. Now, for complex systems, it's always useful to have a performance model right from the architecture stage. Even if it's a simple Excel sheet, it need not be complex performance tools or modeling tools, but you could simply have a very basic kind of a model looking at how frequently does a service be called, what is the complexity of the service or the cost of invoking the service. And if you get the arithmetic right, that's on point number 8, that's what we call as demand. That look at optimization by demand, how frequently is something called and how costly it is to invoke the service. And it is not necessarily that the highest frequency would need to be optimized or the most costly service needs to be optimized. What needs to be optimized is the multiplication of these two. How frequently does something occur and how costly it is. And that is the demand that needs to be targeted first, because the region of highest demand is going to be a bottleneck. Now, coming to point number 9, a lot of IT systems are not necessarily compute intensive like high performance computing, which you may use in fluid dynamic simulations or in a lot of financial risk management applications. But a lot of IT systems would be some things that take inputs from a user at the front end and either read from a database or write to a database as transactions, and the middle tier is used to manage transactions and to cache data, but essentially you have a lot of flow of data through the middle tier. And all of this adds up to communication costs. I mean, you would be surprised to know that the most costly operation in a Java server or a J2E server is not necessarily your servlet calls or JSP calls. It happens to be JDBC calls. Why? Because you need to communicate with the database, and that is a very heavy implementation. So make sure that a lot of communication has been optimized and there's not a redundant communication happening that can cause your architecture to fall flat. You also need to keep in mind, as point number 10 is, that as your system gets complex, it's going to be more and more difficult to debug what's going on. And there is a tendency to use a lot of third-party tools and take a variety of them, and each would have their own formats, and then during implementation you will log some of them. Then you need something that can talk to all the tools, get it all together. So it's always good that during the architecture stage you build your instrumentation architecture frameworks and make sure, whether it is homegrown or uses third-party tools, that you have identified which points need to be instrumented. You've identified the cost of instrumentation. You've also defined where all you can dynamically switch on instrumentation wherever required, and then decide what kind of tools and homegrown solutions are going to work for the same, so that you have a holistic way to look at performance all throughout your application end to end. Point number 11 is also important for systems as they grow and as they start moving from development to a maintenance phase. That once you are in the maintenance phase, you are not necessarily going to have the best people who had initially developed your project. So you need to make sure that any design optimizations for a system under maintenance can cause side effects, and we'll see an example of that as well as we progress. And you better be aware of what are the side effects and how do you deal with them. For any mission critical system, once you build a model, then you need to look at quantitative analysis of the architecture. You need to prove that the architecture is going to work, is going to perform, is going to scale. You've identified all the alternatives through a simple quantitative analysis. You could use modeling tools, or you could build a simple model in Excel as well. Point number 13 is also important, that if you are done with the architecture, you as an architect are quite clear how things are going to perform. But whatever solutions you come up with, they have to be implemented. They have to be implemented by developers. Now, if you have an end-to-end performance requirement for throughput and response time, how does it translate into targets for developers who will work with individual service calls and individual database calls? How do you translate an end-to-end response time of 2 seconds for 5,000 concurrent users into a developer who works as a single user and needs to know that a given SQL should finish in how many milliseconds? Now, there are simple techniques to do that. We'll not get into that right now, but just keep in mind is that only if you're able to meaningfully translate these requirements can you really do a good job of optimization at the development stage. The last point, as a general guiding principle that I'll touch upon, is that never try to over-engineer for performance during the initial implementation. I mean, yes, you need to make sure performance will be met, but you also need to make sure is that systems will keep changing and you'll keep having workload growth as time progresses. So rather than try to over-engineer initially, you need to make sure that you have the right controls available and the right options thought about, that in the future, if time permits and if really the need is felt for it, you would like to invoke a certain option that is available. So it's better to think of number of options, document them, but actually choose only the one that is simplest and close to optimal for a given instant of time, rather than try to give all the engineering upfront and make the system more and more complex. So we'll see an example of that as well.